Hello, my name is Kaylin Ebener, and this is my fourth lab, Oscillations. In my presentation, I will be discussing how I observed a real-life system, created the computer model in GlowScript, and compared my real-life observations to the computer model. Then I will discuss the physics principles involved. The first goal in this lab was to implement the energy principle, which gives us delta E is the total change in energy equals the change in kinetic energy plus the change in potential spring energy plus the change in gravitational potential energy. I will then analyze a given video and tracker to find positional data, which I will use in my GlowScript model to find the kinetic, spring potential, and gravitational potential energies with the formulas listed above. With these, I will be able to update the total energy, velocity, and position data, and iterate this process at each timestamp. Lastly, I will compare the computer model to the observed data. Here is a description of the system. This is the video of motion that I analyzed in Tracker. Note that there is both X and Y direction movement. I oriented Tracker by setting the origin at the spring's attachment point. I calibrated the video with the known length of the stretched spring. My initial position was found in the table in the bottom right corner, and my initial velocity was 0 because the weight on the spring started from rest. The period of oscillation, t, was 1.614 seconds, and I found that by taking the average of the times of the first 3 full oscillations that I got by looking at both the time versus x position and time versus y position graphs' lowest points. In my GlowScript model, I used an average of the periods of oscillation obtained from both the time versus x position and time versus y position graphs. This was to obtain the best period of oscillation for both the x and y directions. If I had used the average of the first 3 oscillation periods from the x position graph only, there would be a lower accuracy of the model in the y direction, and vice versa. It is important to use the average since the value of t affects values such as k, L naught, and the spring force and net force, as seen in the equations below. I initialized my GlowScript program to the weight's mass, position, and initial velocity, and the video's time range from Tracker. The initial time was 0, and the time step was 1/210, which was about half of the video frame rate in Tracker. To factor in the observed positional data into my model, I input the x and y positions from Tracker by importing a CSV file with the data points from Tracker. G was the universal gravitational constant, K is the spring constant, and L naught is the length of the relaxed spring. These calculated values were found from manipulations of existing equations. K was calculated from the formula below, where T is the period of oscillation and K equals 7.642. L naught was calculated with the equation L, the current length of the spring, minus the mass times G over K. With everything plugged in, L naught equals 0.184 meters. S is in the spring potential energy equation and is equal to the magnitude of L minus L naught. At the bottom of the slide are the code for finding the different energies according to equations on the goals of the lab slide. The only new one is E, which stands for total energy, and is calculated by adding up the kinetic, gravitational potential, and spring potential energies. In the while loop of the code for each time step, I calculated the gravitational and spring forces to find the net force. I updated the object's velocity and position from this data, and then updated the spring information based on the new position of the weight on the end. After that, I calculated the kinetic, gravitational, spring, and total energies and their changes. This is my GlowScript program running. The animation shows the model ball in blue and the experimental ball's position in red. You can see that their paths are very similar, indicating that the model is a pretty good representation of the observed position. Next is the graph of the different energies with spring potential in green, gravitational potential in red, kinetic in blue, and total in orange. You can see that changes in spring and gravitational potential energies are mirrors of each other, while the change in total energy is 0, both as expected. Lastly, you see the graphs of the model in blue versus experimental in red positions for both the x and then y positions. As you can see, the change in energy versus time graph above shows that the total energy stays at 0 through the duration of the observed and modeled motion, meaning, in this case, the sum of the changes in gravitational potential, spring potential, and kinetic energies are 0. Because of this, we know that there are no outside forces acting on the system and the energy principle is satisfied. Here are the two position versus time graphs produced by the model, x on the left and y on the right. The model should have been equally accurate in matching the experimental positions for both the x and y directions due to the period being the average of the periods calculated from both datasets. However, you can see that the x position data is a slightly better match, and this could have been due to calculation or other unknown errors. Since the y position observed in model data did not match, one could weight the average time period used in calculating the spring force constants. A better camera with more frames per second could have also been used for more accurate position data. Also, the total energy calculation could be tweaked to include changes in energy due to other forces like air resistance. In this lab, we accomplished all our goals. The main idea was to implement the energy principle by analyzing a video, then using code to find the necessary data to find and update kinetic, spring potential, and gravitational potential, and total energies with each time step. We then compared the computer model and observed data, all while gaining a better understanding of the energy principle. Thank you for watching!